In hydrologic analysis, it is essential that one is able to estimate peak discharge. Calculating peak discharge is key to hydrologic design because flow gauges are not always located everywhere. For example, you need to size a catch basin on a road, but there are no runoff gauges located on the road itself. In this lesson on peak discharge, there are two key learning objectives. The first objective is to understand and evaluate calibrated hydrologic models used to estimate peak discharge. Calibrated models are based on gauged watersheds. The second objective is to understand, evaluate, and calculate flows based on uncalibrated hydrologic models. Uncalibrated models are used when calibrated models are not available, and especially for design purposes. Calibrated models are very useful in professional work and will be helpful in your professional careers. So what is peak discharge? Peak discharge, also referred to as peak flow rate, is the maximum water surface elevation within a cross-section of a river. It can also be the maximum volumetric flow rate that passes a particular location. It is essential that we determine peak flow rate because peak flow rate is used for design of various stormwater facilities, such as swales, culverts, gutters on roads, catch basins, and pipes, to name a few. So let's start with talking about a calibrated model. First, calibrated models are very useful in large watersheds. These are usually large regional watersheds, not land development or roadway projects, which range in size from a few square feet to 1,000 acres. Second, we need to obtain annual maximum peak discharge for the gauges in each of these regional areas. For example, here is an image of LA Basin in Southern California. We can obtain gauge data for various locations within this watersheds to calibrate and develop an LA model. Next, we're going to measure the various watershed characteristics and meteorological characteristics, such as watershed area, slope, length of the watershed, annual rainfall. Then we're going to perform flood frequency analysis on each of the watershed gauges. Finally, it's time to perform a multivariable regression. Note, in hydrology, this regression is usually displayed by a power equation, as shown. I will create a supplemental video in the coming weeks to demonstrate how you can create a multivariable regression. Next, there are many uncalibrated models, but in today's lesson we will cover two different methods. The first method and most widely used is the rational method. It is ideal for watersheds that are smaller than 640 acres. But determine if this method is valid. For your project, you will need to refer to the local hydrology manual. In Southern California, most of the manuals state 640 acres as an acceptable size. The general equation for the rational method is the flow rate Q is equal to C, the runoff number for the rational method, which is unitless, I, the rainfall intensity, which is measured in inches per hour, and A, the area of the watershed. The value of the runoff number for the rational method can be determined from a table as shown. You can also find this table in your note packets. Please note that the C value, or the rational method coefficient, is not the same as the curve number or CN value discussed previously in class. The C value for the different varies for different land usages, soil types, and slopes. In addition, for each land use, there are two rows of data. The first row is for runoffs less than a 25-year storm, while the second row is for flows greater than or equal to a 25-year storm. I, the rainfall intensity, is determined based on the travel time, and you use an IDF curve to determine the intensity, and the watershed area is measured using AutoCAD or another various tool. The wonderful part about this equation is that there is no need for any unit conversion. By simply using this formula, your final answer will be given to you in cubic feet per second. Most watersheds are not homogeneous. What I mean is there's not a single C value. Thus, you will need to calculate a composite rational method runoff coefficient. Once the weighted rational method coefficient is determined, the flow rate for the watershed is determined by multiplying the weighted coefficient by the rainfall intensity and the total watershed area. Or you can pull the rainfall intensity for the watershed out of the equation and multiply each individual coefficient to its area and sum these values to get the total runoff. Let's start an example. I'd like you to finish this in class, but we're given a location in the mountainous region of Orange County. There is a proposed development on 25 acres of land. You previously determined the time of concentration of the existing watershed as 60 minutes, and for the developed watershed is 40 minutes. I want you to determine the pre and post flow rates for a 10-year storm event. So the first step is to determine all your C values. So let's see how to find those. The first land use is a meadow. Since we aren't given a soil type, we will assume we have a soil type of C. The slope for meadows is 2 to 6%. We will assume 0.28. Oh, sorry, not assume 0.28. Because we have a slope of 2 to 6% and we have a recurrence interval of a 10-year storm, the first row and the middle column gives us 0.28. Next, we need to determine the rainfall intensity. This is done by going to the Orange County mountainous IDF curve. For each travel time, you will find the rainfall intensity. Thus, for the existing condition or pre-developed condition, we go to 60 minutes, and for a 10-year storm event, we have a runoff coefficient of about we have a rainfall intensity of about 1.25 inches per hour. Finally, you need to calculate the overall flow rate. For this example, for the 1-acre residential lots and for the streets, assume a slope of 1% and finish the calculations. Next, let's look at subdividing a watershed. Subdividing a watershed is a very important part. If you have a watershed that's given as shown, you have 3 subdivided areas. We need to calculate the peak discharge for each of the inlets. And we need to calculate the peak discharge for each of the pipes. Note, when calculating discharge for the pipes, you cannot simply add the inlet discharge. You need to determine the longest time and calculate the overall discharge. So let's look at an example to kind of walk you through how this works. Based on the example of the previous slide, you have a 3-area subdivided watershed. The watershed is located in Maryland, and we are going to do our design based on a 50-year storm. To calculate the flow rates, we need to first determine the intensities, rainfall intensity for each of the basins and pipes. So, For inlet 1, we have a travel time of 5 minutes. If we use the IDF curve, we determine at 5 minutes we have a rainfall intensity of 10 inches per hour. Repeat this for each of the other remaining inlets. At 6 minutes, we have 9.5 inches per hour, and at inlet 3, 7 minutes, we have 9 inches per hour. Next, we're going to go to the pipes. Pipe 1 refers to the pipe after area A1 and A2 are combined. We compare the travel times in area A1 and A2. In order to calculate the governing intensity, we pick the longest travel time, which in this case would be for area 2 or 6 minutes. Thus, we will use 9.5 inches per hour when we calculate the flow rates for pipe A. Next, pipe B is the pipe located after area 3. We need to determine the longest travel time to pipe 2. This is determined by looking at area A1 and A2 and determining which time is the longest, in this case 6 minutes, and adding it to the travel time within pipe A, which is 4 minutes. We get 10 minutes. Since 10 minutes is greater than 7 minutes, we know that the 10 minutes will govern. And we have a rainfall intensity of 8 inches per hour. Now we're ready to calculate our flow rates. For inlet 1, Q equals CIA. The C is 0.6, the intensity is 10 inches per hour, and the area is 2.8. Thus, we get 17 CFS. We repeat this similarly for inlets 2 and inlet 3. Next, we look at pipe 1. Remember, we're combining areas A1 and A2. As I mentioned previously, the rainfall intensity is constant for both areas when sizing a pipe. Thus, we have 9.5 times the coefficient for A1 times the area for A1 plus the coefficient for A2 times the area for A2, and we get 31 CFS. If we had simply added the flows of inlet 1 and inlet 2, we would have gotten a higher flow rate and resulted in an over-design. Next, for pipe B, we have 3 areas combining. Again, we determined that 8 inches per hour is our governing intensity, and we have 3 distinct areas and coefficients that we multiply and sum together to get 41 CFS. I'd like you to try and do this exercise for this example with 4 subbasins. The site is still located in Baltimore, Maryland, but this time I want you to calculate the 25-year flow rate for each inlet and for each of the 3 pipes, the pipe leaving area A1, the pipe leaving area A2 and A3, and the pipe that leaves A4. It should be noted, as you move down the line, all the areas are combining. Thus, pipe 1 only contains area A1, while pipe 2 contains area A1, A2, and A3, and pipe 3 contains area A1, A2, A3, and A4. If you have questions, please bring those to class. Next is the slope area method. This method is quite unique. This method is used to estimate flows within an ungauged river. In order to measure the flows, you will need to survey the river. As shown, we are surveying the upstream cross-section AA and the downstream cross-section BB. The first step is to measure the flow area and wetted perimeters. Next, we're going to calculate the upstream and downstream conveyance, which is 1.49 divided by the Manning's roughness times the cross-sectional area multiplied by the hydraulic radius raised to the 2/3 power. Next, we're going to calculate the composite or overall conveyance, which is multiplying the upstream and downstream conveyance and square rooting it. The fourth step is to measure the water surface slope. This is the change in elevation between cross sections A and B at the water surface divided by the length. The fifth step is to estimate a discharge, where we take the conveyance coefficient and multiply it by the water surface slope. This equation should look very similar to you. It's the Manning's equation. But wait, there's a catch. The Manning's equation is not based on a water surface slope. It's based on a friction slope. So the sixth step is to correct for energy and calculate the friction slope. The first part of the equation is how you calculate the velocity head. It includes the flow rate that calculated in step 5, gravity, and the cross-sectional areas of the upstream and downstream cross-sections. The friction slope is determined by adding the change in elevation of the water surface plus the velocity head divided by the length between cross-section AA and BB. The final step is to calculate the corrected flow rate, which is the conveyance coefficient in step 3 multiplied by the friction slope to the 1/2 power in step 6. We will do more examples in class, and we will test some of the slope area method as well.